It is generally incorrect to install a 20 amp receptacle on a 15 amp circuit. This is primarily due to safety concerns, National Electrical Code violations, and the potential for misleading information. Firstly, safety is paramount. Installing a 20 amp receptacle on a 15 amp circuit could lead to an overload and create a fire hazard. The circuit wiring, switches, and all other components are rated for a maximum of 15 amps. Using a 20 amp receptacle could allow devices to draw more current than the circuit is designed to handle, potentially causing overheating and damage. Secondly, it would violate the National Electrical Code. Article 210.21b3 of the National Electrical Code explicitly states that receptacles installed on 15 amp branch circuits shall not have an ampere rating greater than 15 amps. This code is in place to ensure electrical safety and prevent hazardous situations. Thirdly, using a 20 amp receptacle on a 15 amp circuit can be misleading. It might lead individuals to believe that they can plug in devices that require a 20 amp circuit. This could inadvertently cause overloads and other electrical hazards, as the circuit is only rated for 15 amps. There are a few exceptions to this general rule. Firstly, a dedicated circuit may use a 20 amp receptacle. Where the circuit is used exclusively for a single appliance or device that requires 20 amps, such as a window air conditioner or oven, it's permissible. However, this must be a dedicated circuit specifically designed for that purpose. Secondly, in kitchens, National Electrical Code Section 210.52d allows for 20 amp rated receptacles on kitchen countertops. However, even in this case, the total load on the circuit must not exceed 80% of the circuit's ampacity. For a 15 amp circuit, this means the total load should not exceed 12 amps. In all other scenarios, it is not permissible to install a 20 amp receptacle on a 15 amp circuit. Adhering to the National Electrical Code and following proper electrical practices are crucial for ensuring the safety and reliability of electrical systems. The National Electrical Code, or NEC, provides comprehensive guidelines for electrical installations to minimize risks. Article 210 covers branch circuits, which are the circuits that supply power directly to outlets and lighting. Several sections within Article 210 are relevant to receptacle installation and circuit loading. Firstly, 210.19 addresses conductor sizing for branch circuits. It specifies the minimum size of conductors required based on the circuit's overcurrent protection rating. For a 15 amp circuit, typically 14 American wire gauge copper wire is used, while a 20 amp circuit usually requires 12 American wire gauge copper wire. Secondly, 210.20 discusses overcurrent protection. This section emphasizes the importance of protecting branch circuits with the appropriate size circuit breaker or fuse. The overcurrent protection device should match the ampacity of the circuit wiring to prevent overloads. Thirdly, 210.21b focuses on receptacle ratings. As previously mentioned, 210.21b3 specifically prohibits installing receptacles with a higher ampere rating than the branch circuit's rating on 15 amp circuits. Fourthly, 210.23 covers permissible loads. This section outlines the types of loads that can be connected to branch circuits, depending on their ampere rating. For a 15 amp circuit, the total load should not exceed 80% of the circuit's rating, which is 12 amps. Fifthly, 210.52 deals with receptacle placement in dwelling units. This section specifies requirements for receptacle spacing along walls and countertops in kitchens, living rooms, and other areas to ensure convenient access to power. Understanding and adhering to these sections of the National Electrical Code is essential for safe and compliant electrical installations. Using the correct size wire for the circuit's ampacity is critical for preventing overheating and potential fires. Overloading a circuit can cause the wires to heat up, which can damage insulation and create a fire hazard. The National Electrical Code specifies the appropriate wire gauge for different circuit ratings to ensure that the wiring can safely handle the expected current. The ampacity of a wire refers to the maximum amount of current, measured in amps, that a conductor can carry continuously without exceeding its temperature rating. The National Electrical Code provides tables that list the ampacity of different wire sizes and types. For example, Table 310.15b16 in the NEC lists the allowable ampacities of insulated conductors rated up to 600 volts. For typical household wiring using copper conductors with insulation types such as THHN or THWN, the ampacity values are as follows. Firstly, 14 American wire gauge copper wire, commonly used for 15 amp circuits, has an ampacity of 15 amps. Secondly, 12 American wire gauge copper wire, commonly used for 20 amp circuits, has an ampacity of 20 amps. Thirdly, 10 American wire gauge copper wire, often used for 30 amp circuits, has an ampacity of 30 amps. Using a wire with a lower ampacity than the circuit's overcurrent protection rating is a code violation and a significant safety hazard. If a 15 amp circuit is wired with 16 American wire gauge wire, which has a lower ampacity than 15 amps, the wire could overheat and potentially cause a fire if the circuit is fully loaded. Similarly, using 14 American wire gauge wire on a 20 amp circuit is also dangerous because the wire is not designed to handle that much current continuously. It's crucial to select the appropriate wire size based on the circuit's ampacity and the expected load to ensure safe and reliable electrical operation. When determining the correct wire size for an electrical circuit, it's important to consider several factors, including the circuit's ampacity, the ambient temperature, and the number of current-carrying conductors in a raceway or cable. The National Electrical Code provides guidelines and tables to help ensure that the selected wire size is adequate for the intended application. Firstly, determine the circuit's ampacity. The circuit's ampacity is determined by the overcurrent protection device, such as a circuit breaker or fuse. For example, a circuit protected by a 15 amp circuit breaker has an ampacity of 15 amps. Secondly, select the appropriate wire size based on the ampacity. Refer to Table 310.15b16 in the National Electrical Code to determine the minimum wire size required for the circuit's ampacity. For example, if the circuit has an ampacity of 15 amps and uses copper conductors with THHN insulation, 14 American wire gauge wire is typically sufficient. Thirdly, apply ampacity correction factors for ambient temperature. If the ambient temperature is higher than 30 degrees Celsius, 86 degrees Fahrenheit, the ampacity of the wire must be reduced according to the correction factors provided in Table 310.15b2 of the National Electrical Code. This is because higher temperatures can reduce the wire's ability to dissipate heat, potentially leading to overheating. Fourthly, apply ampacity adjustment factors for the number of current-carrying conductors. If multiple current-carrying conductors are installed in a raceway or cable, the ampacity of each conductor must be reduced according to the adjustment factors provided in Table 310.15b3 of the National Electrical Code. This is because the heat generated by multiple conductors in close proximity can raise the overall temperature and reduce the wire's ampacity. Fifthly, consider voltage drop. Voltage drop occurs when the voltage at the load is lower than the voltage at the source due to the resistance of the wires. The National Electrical Code recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. If the voltage drop is excessive, a larger wire size may be required to reduce the resistance and maintain adequate voltage at the load. By carefully considering these factors and consulting the National Electrical Code, it's possible to select the appropriate wire size for an electrical circuit and ensure safe and reliable operation. Receptacles are designed with different configurations based on their amperage and voltage ratings. These configurations, standardized by the National Electrical Manufacturers Association, or NEMA, ensure that devices are plugged into circuits with the appropriate voltage and current capacity. Firstly, NEMA 5-15 receptacles are standard 15 amp 125 volt receptacles. They have two parallel slots and a U-shaped grounding slot. These receptacles are commonly found in homes for general purpose use. Secondly, NEMA 5-20 receptacles are 20 amp 125 volt receptacles. They have one parallel slot and one T-shaped slot along with a U-shaped grounding slot. The T-shaped slot allows both 20 amp and 15 amp plugs to be inserted. Thirdly, NEMA 6-15 receptacles are 15 amp 250 volt receptacles. They have two parallel, non-coplanar blades and a grounding pin. These receptacles are typically used for specific appliances that require 250 volts. Fourthly, NEMA 6-20 receptacles are 20 amp 250 volt receptacles. They have two parallel, non-coplanar blades and a grounding pin. One of the blades is T-shaped to accept both 20 amp and 15 amp plugs. Fifthly, NEMA 14-30 receptacles are 30 amp, 125 or 250 volt receptacles. They have two vertical blades, one L-shaped blade, and a grounding pin. These receptacles are commonly used for electric dryers. Sixthly, NEMA 14-50 receptacles are 50 amp, 125 or 250 volt receptacles. They have two vertical blades, one L-shaped blade, and a grounding pin. These receptacles are often used for electric ranges and some electric vehicle chargers. Each NEMA configuration is designed to prevent accidental insertion of plugs into receptacles with incompatible voltage or amperage ratings. Using the correct type of receptacle for the intended application is essential for electrical safety and compliance with the National Electrical Code. Overloading a circuit can have serious consequences, ranging from nuisance tripping of circuit breakers to dangerous electrical fires. Understanding the causes and effects of overloading is crucial for preventing these hazards. Firstly, overloading occurs when the total current drawn by devices connected to a circuit exceeds the circuit's rated ampacity. This can happen when too many appliances or devices are plugged into the same circuit, or when a single device draws an excessive amount of current. Secondly, the effects of overloading can include overheating of wires and components. When a circuit is overloaded, the wires and other components can heat up due to the excessive current flow. This heat can damage the insulation on the wires, leading to short circuits and potential fires. Thirdly, circuit breaker tripping is a common consequence. Circuit breakers are designed to protect circuits from overloads by automatically tripping when the current exceeds the breaker's rating. This is a safety mechanism to prevent overheating and potential fires. Fourthly, equipment damage can result from overloading. Overloading can damage appliances, electronics, and other devices connected to the circuit. The excessive current can cause components to fail prematurely, leading to costly repairs or replacements. Fifthly, electrical fires are a serious risk. If a circuit is severely overloaded and the circuit breaker fails to trip, the excessive heat can ignite nearby combustible materials, leading to an electrical fire. Sixthly, preventing overloads involves several strategies. Distributing the load across multiple circuits is a key strategy. Avoid plugging too many devices into a single circuit. Use multiple circuits to distribute the load more evenly. Using power strips with built-in circuit breakers can help. These power strips can provide additional protection against overloads by automatically shutting off power to the connected devices if the current exceeds a safe level. Checking the power requirements of appliances is also important. Before plugging in an appliance or device, check its power requirements, typically listed in watts or amps on the device's nameplate. Ensure that the total load in the circuit does not exceed the circuit's rated ampacity. Avoiding using extension cords is recommended when possible. Extension cords can increase the risk of overloading a circuit, especially if they are undersized or damaged. Plug appliances directly into wall receptacles whenever possible. By understanding the causes and effects of overloading and implementing preventive measures, it's possible to minimize the risk of electrical hazards and ensure the safe operation of electrical systems. Grounding is an essential safety feature in electrical systems, providing a path for fault current to flow back to the source and trip the circuit breaker, thereby protecting people and equipment from electrical shock. Understanding the principles and components of grounding is crucial for ensuring electrical safety. Firstly, grounding provides a low impedance path for fault current. When a fault occurs, such as a short circuit between a live wire and a metal enclosure, the grounding system provides a low resistance path for the fault current to flow back to the source. This high fault current causes the circuit breaker to trip quickly, disconnecting the power and preventing electrical shock. Secondly, grounding protects against electrical shock. By providing a path for fault current, the grounding system helps to prevent dangerous voltages from appearing on metal enclosures or other conductive surfaces. This reduces the risk of electrical shock if someone comes into contact with a faulty appliance or equipment. Thirdly, the grounding electrode system is a key component. The grounding electrode system consists of one or more grounding electrodes, such as ground rods, ground plates, or metal underground water pipes that are connected to the earth. This system provides a connection to the earth, which serves as a reference point for electrical potential and helps to stabilize the voltage of the electrical system. Fourthly, the equipment grounding conductor, or EC, connects the metal enclosures of electrical equipment to the grounding electrode system. This conductor provides a low impedance path for fault current to flow back to the source, ensuring that the circuit breaker trips quickly in the event of a fault. Fifthly, the grounded conductor, or neutral, is connected to the grounding electrode system at the service entrance. This conductor carries the return current from the load and also provides a path for fault current to flow back to the source. Sixthly, proper installation and maintenance are essential. Proper installation and maintenance of the grounding system are crucial for ensuring its effectiveness. All connections must be tight and corrosion-free, and the grounding electrodes must be properly installed and maintained to provide a reliable connection to the earth. By understanding the principles and components of grounding and ensuring proper installation and maintenance, it is possible to provide a safe and reliable electrical system that protects people and equipment from electrical shock. Ground fault circuit interrupters, or GFCIs, are life-saving devices that protect people from electrical shock by monitoring the current balance in a circuit and quickly disconnecting the power if a ground fault is detected. Understanding how GFCIs work and where they are required is essential for electrical safety. Firstly, GFCIs detect ground faults. A ground fault occurs when current leaks from a live wire to ground, such as through a person's body. GFCIs are designed to detect these ground faults by monitoring the current flowing through the hot and neutral wires of a circuit. Secondly, GFCIs work by measuring current balance. GFCIs contain a differential transformer that measures the current flowing through the hot and neutral wires. In a normal circuit, the current flowing through the hot wire should be equal to the current flowing through the neutral wire. If there is a ground fault, some of the current will leak to ground, causing an imbalance between the hot and neutral currents. Thirdly, GFCIs trip quickly. When a ground fault is detected, the GFCI trips the circuit within milliseconds, quickly disconnecting the power and preventing electrical shock. GFCIs are designed to trip at a current imbalance of 5 mA or less, which is well below the level that can cause serious injury. Fourthly, GFCIs are required in certain locations. The National Electrical Code requires GFCIs in certain locations where there is a high risk of electrical shock, such as bathrooms, kitchens, outdoor receptacles, and construction sites. These locations are typically wet or damp, which increases the risk of electrical shock. Fifthly, GFCIs are available in different types. GFCIs are available in different types, including receptacle type GFCIs, circuit breaker type GFCIs, and portable GFCIs. Receptacle type GFCIs are installed in place of standard receptacles and provide protection for that specific outlet. Circuit breaker type GFCIs are installed in the electrical panel and provide protection for the entire circuit. Portable GFCIs can be plugged into standard receptacles and provide temporary GFCI protection. Sixthly, regular testing is important. Regular testing of GFCIs is essential to ensure that they are functioning properly. GFCIs should be tested monthly by pressing the test button on the device. If the GFCI does not trip when the test button is pressed, it should be replaced immediately. By understanding how GFCIs work and where they are required, it's possible to provide a safe electrical environment and protect people from electrical shock. Arc fault circuit interrupters, or RFCIs, are devices that protect against electrical fires by detecting arc faults, which are dangerous electrical discharges that can occur in damaged or deteriorated wiring. Understanding how FSIs work and where they are required is essential for fire safety. Firstly, FSIs detect arc faults. Arc faults are unintentional electrical discharges that can occur when wiring is damaged, loose, or corroded. These arc faults can generate high levels of heat, which can ignite nearby combustible materials and cause a fire. FSIs are designed to detect these arc faults by monitoring the electrical current for unusual patterns or signatures. Secondly, FSIs work by analyzing the electrical current. FSIs use sophisticated algorithms to analyze the electrical current flowing through a circuit. They can distinguish between normal electrical activity and the unique characteristics of arc faults, such as erratic current fluctuations or high-frequency noise. Thirdly, FSIs trip quickly. When an arc fault is detected, the FSI trips the circuit within milliseconds, quickly disconnecting the power and preventing a fire. FSIs are designed to trip at a lower current level than standard circuit breakers, providing enhanced protection against arc faults. Fourthly, FSIs are required in certain locations. The National Electrical Code requires FSIs in certain locations where there is a high risk of arc faults, such as bedrooms, living rooms, and dining rooms. These locations typically have a high concentration of electrical appliances and wiring, which increases the risk of arc faults. Fifthly, FSIs are available in different types. FSIs are available in different types, including circuit breaker type FSIs and receptacle type FSIs. Circuit breaker type FSIs are installed in the electrical panel and provide protection for the entire circuit. Receptacle type FSIs are installed in place of standard receptacles and provide protection for that specific outlet. Sixthly, FSIs provide enhanced fire protection. FSIs provide enhanced fire protection compared to standard circuit breakers. Standard circuit breakers are designed to protect against overloads and short circuits, but they may not detect arc faults. FSIs are specifically designed to detect arc faults and trip the circuit before a fire can start. By understanding how FSIs work and where they are required, it's possible to provide enhanced fire protection and create a safer electrical environment. When working with electrical systems, safety should always be the top priority. Following safe work practices and using appropriate personal protective equipment can significantly reduce the risk of electrical shock, burns, and other injuries. Firstly, always de-energize circuits before working on them. Before starting any electrical work, always de-energize the circuit by turning off the circuit breaker or removing the fuse. Use a voltage tester to verify that the circuit is de-energized before touching any wires or components. Secondly, use lockout-tagout procedures. When working on de-energized circuits, use lockout-tagout procedures to prevent the circuit from being accidentally re-energized. This involves placing a lock and tag on the circuit breaker or fuse box to indicate that the circuit is being worked on. Thirdly, wear appropriate personal protective equipment. When working with electrical systems, wear appropriate personal protective equipment, including safety glasses, insulated gloves, and insulated footwear. These items can protect you from electrical shock, burns, and other injuries. Fourthly, use insulated tools. Use insulated tools with non-conductive handles when working on electrical systems. These tools can help to prevent electrical shock if you accidentally come into contact with a live wire. Fifthly, maintain a safe working distance. Maintain a safe working distance from exposed energized parts. Avoid reaching into or touching energized equipment unless you are properly trained and equipped to do so. Sixthly, never work alone. Never work on electrical systems alone. Always have someone nearby who can assist you in case of an emergency. Seventhly, follow the National Electrical Code. Follow the National Electrical Code and other applicable codes and standards when working on electrical systems. These codes provide guidance on safe work practices and installation methods. Eighthly, be aware of your surroundings. Be aware of your surroundings and identify any potential hazards such as wet floors, overhead power lines, or confined spaces. Take steps to eliminate or mitigate these hazards before starting work. By following these safe work practices and using appropriate personal protective equipment, it's possible to significantly reduce the risk of electrical injuries and create a safer working environment. Electrical panels, also known as breaker boxes or load centers, are distribution points for electricity in a building. They receive power from the utility company and distribute it to various circuits throughout the building. Understanding the components and functions of electrical panels is essential for electrical safety and troubleshooting. Firstly, the main breaker is the primary disconnect for the entire electrical panel. It allows you to shut off all power to the panel in case of an emergency or when performing maintenance. The main breaker is typically located at the top of the panel and has a higher amperage rating than the branch circuit breakers. Secondly, branch circuit breakers protect individual circuits from overloads and short circuits. These breakers are designed to trip automatically when the current exceeds the breaker's rating, preventing overheating and potential fires. Branch circuit breakers are typically arranged in rows and are labeled to indicate which circuits they control. Thirdly, bus bars are conductive strips that distribute power from the main breaker to the branch circuit breakers. Bus bars are typically made of copper or aluminum and are insulated from the panel enclosure. Fourthly, the neutral bus bar is a conductive strip that provides a common connection point for the neutral wires of all the circuits. The neutral bus bar is typically connected to the grounding electrode system. Fifthly, the ground bus bar provides a connection point for the grounding wires of all the circuits. The ground bus bar is typically connected to the panel enclosure and the grounding electrode system. Sixthly, the panel enclosure houses all of the components of the electrical panel and provides protection from physical damage and electrical hazards. The panel enclosure is typically made of metal and is grounded to provide a safe path for fault current. Seventhly, proper labeling is essential for identifying circuits. Each circuit breaker should be clearly labeled to indicate which lights, receptacles, or appliances it controls. This makes it easier to identify and troubleshoot circuits when necessary. Eighthly, regular inspection and maintenance are important for ensuring the safe and reliable operation of the electrical panel. Inspect the panel for any signs of damage such as corrosion, overheating, or loose connections. Tighten any loose connections and replace any damaged components. By understanding the components and functions of electrical panels and performing regular inspection and maintenance, it's possible to ensure the safe and reliable distribution of electricity throughout a building. Voltage drop is a reduction in voltage that occurs along an electrical circuit due to the impedance of the conductors. Excessive voltage drop can cause equipment to malfunction, lights to dim, and motors to overheat. Understanding the causes and effects of voltage drop and how to minimize it is essential for electrical system performance. Firstly, voltage drop is caused by conductor impedance. The impedance of a conductor is its resistance to the flow of alternating current. The higher the impedance, the greater the voltage drop. The impedance of a conductor depends on its resistance, inductance, and capacitance. Secondly, voltage drop affects equipment performance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. Lights may dim, motors may overheat, and electronic devices may not function properly. Thirdly, voltage drop is calculated using Ohm's law. Voltage drop can be calculated using Ohm's law, which states that voltage is equal to current times resistance. The voltage drop in a circuit is equal to the current flowing through the circuit multiplied by the resistance of the conductors. Fourthly, the National Electrical Code recommends limiting voltage drop. The National Electrical Code recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. This helps to ensure that equipment receives adequate voltage for proper operation. Fifthly, minimizing voltage drop involves several strategies. Using larger conductors can reduce voltage drop. Larger conductors have lower resistance, which reduces the voltage drop. Selecting conductors with lower impedance is helpful. Conductors with lower impedance, such as copper conductors, can reduce voltage drop. Shortening the circuit length reduces voltage drop. Shorter circuits have less resistance, which reduces the voltage drop. Reducing the load current helps with voltage drop as well. Reducing the load current reduces the voltage drop. Distributing the load across multiple circuits can also help. Distributing the load across multiple circuits reduces the current in each circuit, which reduces the voltage drop. By understanding the causes and effects of voltage drop and implementing strategies to minimize it, it's possible to ensure that equipment receives adequate voltage for proper operation and to improve the overall performance of electrical systems. Short circuits and ground faults are common electrical faults that can cause damage to equipment, electrical shock, and fires. Understanding the causes and effects of these faults and how to protect against them is essential for electrical safety. Firstly, a short circuit occurs when there is an unintended low resistance connection between two conductors that are supposed to be at different voltages. This can happen when the insulation on wires is damaged, allowing the conductors to come into contact with each other. Secondly, a ground fault occurs when there is an unintended connection between a live conductor and ground. This can happen when the insulation on a wire is damaged, allowing the conductor to come into contact with the grounded surface, such as a metal enclosure or a water pipe. Thirdly, the effects of short circuits and ground faults can be severe. These faults can cause a large amount of current to flow through the circuit, which can overheat wires and components, damage equipment, and cause electrical shock or fires. Fourthly, overcurrent protection devices, such as circuit breakers and fuses, are designed to protect against short circuits and ground faults. These devices automatically trip the circuit when the current exceeds a safe level, preventing overheating and potential fires. Fifthly, ground fault circuit interrupters, or GFCIs, are designed to protect against ground faults. These devices monitor the current balance in a circuit and quickly disconnect the power if a ground fault is detected. Sixthly, arc fault circuit interrupters, or SIs, are designed to protect against arc faults, which are dangerous electrical discharges that can occur in damaged or deteriorated wiring. These devices detect arc faults and trip the circuit before a fire can start. Seventhly, proper wiring practices are essential for preventing short circuits and ground faults. This includes using properly sized conductors, installing wiring in accordance with the National Electrical Code, and protecting wiring from damage. Eighthly, regular inspection and maintenance can help to identify and correct potential problems before they lead to short circuits or ground faults. This includes checking wiring for damage, tightening loose connections, and replacing worn or damaged components. By understanding the causes and effects of short circuits and ground faults and implementing protective measures, it's possible to reduce the risk of electrical hazards and ensure the safe operation of electrical systems.